Welcome to AI Paper Podcasts. You know how large language models, LLMs, they're being pushed more and more to tackle really complex problems. Stuff like advanced math proofs or generating intricate code without bugs. They're getting incredibly smart, but even the best ones can sort of hit a wall.
Yeah.
Especially when they need to explore genuinely new ways of thinking, new paths, instead of just defaulting to what they've seen before.
Right, when the standard approach just isn't cutting it.
Okay, so let's unpack this. Today, we're diving deep into a really fascinating new paper. It's called First Return Entropy-Eliciting Explore, or FR3E for short.
FR3E, yeah. Catchy.
It is, and it's literally hot off the presses, just published yesterday, July 10th, 2025, from researchers at ByteDance, MAP, and the University of Manchester.
A strong lineup.
Definitely. And our mission today is to really understand how this new framework, FR3E, is helping LLMs reason better. It seems to fundamentally change how they explore potential solutions. Think of it like giving the LLM a much smarter compass when it gets lost in a really complex problem space.
That's a good analogy.
So for our 1-minute summary, in a nutshell, you've got LLMs powered by reinforcement learning from Verifiable Rewards, RLVR. They're great for complex reasoning.
Fantastic, yeah.
But the big challenge is this thing called unstable exploration. They don't know how to efficiently try new paths when they get stuck.
Exactly. And the traditional ways of figuring out which step was important or using value models to guess future success, they often fall short.
Right.
What's really cool about FR3E is how it brings in this structured exploration. It finds the exact moments the LLM is most uncertain, the high entropy points in its thinking, and then it does these targeted mini explorations, like little side quests, right from those specific points.
So it's not just blindly flailing around. It focuses its effort where it's least sure, and the results seem pretty compelling. More stable training, which is huge, responses that aren't just longer but actually hang together better, more coherent.
Yeah, coherent reasoning chains.
And, crucially, a much higher rate of completely correct answers from start to finish. It's really about building a more robust, structured way for these models to think and learn. If you're working on complex reasoning tasks, this looks like a big step.
Absolutely.
So let's start with that core problem FR3E is tackling. Why do LLMs get stuck in the first place when they're reasoning? We know reinforcement learning, RL, has been a huge boost.
Oh, definitely a game changer.
Especially for tasks like math problems or code generation. It pushes them past just mimicking training data, right? They learn from trial and error.
But that raises the big question. How do you actually tell the LLM which specific step in a long chain of thought was the key one? The one that led to the right answer, or maybe more importantly, the wrong one.
Yeah.
Because traditional methods like group relative policy optimization, GRPO, they often just assign credit sort of uniformly, based only on the final result.
Which is like telling a whole team, good job, or you failed, without knowing who did what.
Exactly. No specific feedback.
That's just not how humans learn effectively, is it?
Yeah.
If you mess up step 3 in a 10-step math problem, you need to know why step 3 was wrong, not just that the final answer didn't match.
Right.
The paper even mentions this idea of LLMs overthinking, getting bogged down, trying everything instead of focusing where they're actually uncertain.
Precisely. And then you have methods that use a critic model, sometimes called a value model.
To predict future rewards.
Yeah, they try to estimate the value of intermediate steps. But they often struggle with instability, things bouncing around, and they can be computationally really expensive.
Especially with language, right? The action space is huge.
Huge and discrete. Choosing the next word. It's a vast space. So these value models often just don't give you that stable, fine-grained feedback you need for really complex reasoning. They can be brittle or just too costly to implement effectively.
Okay, so that sets the stage perfectly for FR3E and its smarter approach. You mentioned it draws inspiration from First Return, then Explore, from Go Explore.
That's right. Go Explore was originally for really hard exploration problems, think robotics or complex games.
How does that work?
The core idea is brilliant, actually. It first focuses on just finding any way to reach a new, interesting state that's the first return.
Okay.
Once it finds such a state, then it launches a more focused, deeper exploration from that promising spot. It's way more efficient than just exploring randomly, especially when the search space is massive.
Makes sense. Find somewhere interesting, then explore around there.
Exactly. And FR3E cleverly adapts this for LLMs and how they generate text, step by step.
So how does FR3E actually do that adaptation?
Okay, so what FR3E does fundamentally is it looks at reasoning paths that successfully reach the correct answer.
Right, the good trajectories.
And along those paths, it pinpoints the high entropy tokens. These aren't random spots. They are the specific decision points where the model's own output distribution showed it was least certain about the next word.
Where it hesitated, essentially.
Kind of, yeah, where it had multiple plausible options with similar probabilities. And from these points, these high uncertainty junctions, it kicks off targeted partial rollouts, new attempts.
Okay.
And by doing this, it actively constructs new localized feedback signals based on whether those new attempts succeed or fail. It learns directly from exploring its own uncertainty.
So it's not guessing randomly, it's literally asking itself, where was I most unsure? And then focusing its learning efforts right there.
Exactly.
And the fact that it's value model free seems like a big win. No need for that extra, potentially unstable critic model.
Absolutely. It simplifies things. It uses the direct empirical outcomes, did this exploration work or not, as the learning signal. Much more direct.
All right, let's get into the weeds a bit. The inner workings. The paper splits FR3E into two main phases. Phase 1 is first return. How does that kick off?
Okay, first return starts with what they call base trajectory generation. Simple enough. You give the LLM a query, like a math problem, and it just generates its step-by-step reasoning, its first attempt.
Standard output.
Right. Then comes the crucial part, entropy computation. For every single token, every word or symbol in that generated sequence, FR3E calculates the entropy.
Which measures the uncertainty at that point.
Exactly. High entropy means the model was less confident, it had several choices it considered nearly equally likely. Low entropy means it was pretty sure what to generate next. These high entropy spots become your candidates for exploration.
And you can actually see this, right? Like words that signal uncertainty.
Yeah, figure 2 in the paper shows this well. High entropy tokens are often words like since, thus, however, maybe, words that introduce logical forks or express uncertainty.
Makes sense.
Whereas low entropy tokens might be specific math symbols or numbers where there's usually only one correct choice in context.
That's really cool. It's like the model flags its own points of confusion. So once it has these high uncertainty points, what's next?
It uses them for semantic block and state construction. Basically, these high entropy tokens act as natural breaking points. They segment the whole reasoning path into smaller, meaningful chunks or blocks.
Like paragraphs in the reasoning.
Sort of, yeah. Each block leads up to one of these uncertain decision points, and the end of each block defines an intermediate reasoning state, a snapshot of the model's thinking right before it had to make a tricky choice.
Okay, so it identifies the uncertain spots and creates these snapshots. That leads us into phase 2, Entropy-Eliciting Explore, the targeted diversification part.
Precisely. Now, from each of those intermediate states, those snapshots, FR3E launches multiple different rollouts. It essentially tells the model, okay, you were uncertain here. Try continuing the reasoning in a few different ways from this exact point.
Exploring the alternatives.
Exactly. And for each of these new paths, it checks the final answer. Simple binary reward. 1 if it's correct, 0 if it's wrong.
Okay, very straightforward feedback.
Very. And this lets it calculate an empirical value for each of those intermediate states it started from. It's basically asking, on average, how successful were the explorations we started from this particular point of uncertainty?
So it quantifies the value of exploring from that specific uncertain juncture.
Exactly. And that value becomes a direct signal to update the model's policy. It learns which uncertain points tend to lead to better outcomes if explored correctly.
And then there's this other piece, the adaptive advantage modulation. That sounds important for stability. RL training can be notoriously unstable.
It's absolutely crucial. This adaptive factor, they call it alpha, intelligently scales the learning signal based on progress.
How does that work?
Okay, so if the reasoning quality is actually improving from one state to the next along the original path,
Things are going well.
right, then alpha actually reduces the impact of the learning signal, even if the explorations found something good. It damps it down slightly.
Why do that?
To prevent the model from getting too confident too quickly, it preserves exploration, stops it from just latching on to the first good thing it finds and ignoring other possibilities, keeps the policy diverse.
Okay, prevents overfitting to early successes.
Exactly. But conversely, if the performance is stagnating or even getting worse between states,
Hitting a rough patch.
then alpha amplifies the learning signal. It says, okay, we're stuck here. We need to learn more strongly from any successful explorations we find. It pushes the model to explore more aggressively right where it's struggling.
So it dynamically adjusts how strongly the model learns based on whether it's making progress or getting stuck.
Precisely. It helps maintain that crucial policy diversity and fights against entropy collapse, where the model just becomes deterministic and stops trying new things.
That's really elegant, like a smart thermostat for the learning process, keeping it in the right zone. Prevents it getting stuck in those local optima.
Yeah, it's a neat mechanism for stable, ongoing learning.
All right, let's talk results. The proof is in the pudding, as they say. How did FR3E actually perform? You mentioned they tested on Qwen 2.5 models.
Right. Qwen 2.57b, the 7b math variant, and the bigger 32b model, they compared it against GRPO++ way, which is a strong baseline method. A mix. Some lower difficulty math problems from Deepscaler, and then higher difficulty ones from Simple RL to really test the complex reasoning. And they evaluated on standard benchmarks like AME24, GSM-8K, math, etc.
Okay, comprehensive setup. What was the first key finding?
Healthier exploration. Looking at the entropy loss curves, particularly figure 3 in the paper, FR3E consistently keeps the model's entropy higher than GRPO++.
Meaning it keeps exploring more.
Exactly. Especially for the specialized Qwen 2.5 Math 7b model, GRPO++ entropy just plummets really quickly. FR3E maintains that diversity, that ability to explore different paths for much longer. And that's vital for complex problems where the first idea might not be the best.
Avoids that premature convergence, that entropy collapse.
Yeah.
Okay, makes sense. What else?
Higher overall performance. If you look at Figure 4 and Table 1, FR3E generally leads to better scores on the benchmarks, like AME24.
So it finds better solutions more often.
Yes, but what's really interesting is where the biggest gains were. While it definitely helped the specialized math model,
The Qwen 2.5 Math 7b.
right, the improvements were actually more pronounced for the general purpose 7b and the big 32b models.
Huh. Why do you think that is?
Well, it suggests that this kind of structured RL exploration is maybe most effective for generalist models. They have broader knowledge, but might lack the super specialized reasoning pathways. FR3E helps them build those pathways effectively.
Whereas the specialized model might already be quite good, so the RL needs more careful tuning.
Potentially, yes. Its strong priors might interact differently with the RL signal. It's a nuanced finding, suggesting tailored approaches might be needed depending on the base model.
Interesting. Okay, finding 3. Stable training and consistent reasoning.
Yes, several points here. First, the advantage estimates, shown in Figure 5. FR3E's estimates are much more stable, staying tightly clustered around 0.
Unlike the baseline.
Right, which showed more variance. This stability in the advantage signal translates directly to a more stable, predictable training process overall. Less bouncing around.
Which is great for practical application. What else?
Longer responses. Figure 6 shows FR3E models generate significantly longer reasoning chains. This isn't just rambling. It indicates they're capable of developing more extended, coherent lines of thought.
Or deeper reasoning.
Exactly. And maybe most critically, look at figures 7 and 8, which track fully correct versus fully wrong trajectories. FR3 dramatically increases the number of completely correct reasoning paths.
Start to finish, every step right.
Yes, and it simultaneously suppresses the completely wrong ones. It's not just getting the final answer right more often by luck, it's getting the entire process right more consistently.
That suggests it's really learning the underlying logic better.
It strongly points that way. The algorithm is guiding the policy towards high-quality, reliable reasoning.
And those heat maps in Figure 9, they looked compelling too.
They really drive it home. FR3E shows this clear progression during training, low accuracy turning into high accuracy on problems. And once it learns a problem, that knowledge seems to lock in. It stays accurate.
It doesn't forget or fluctuate like the baseline seemed to.
Right. GRPO++ showed more variability, sometimes getting a problem right, then wrong again later. FR3E's learning seems more robust, more internalized. It really gets the solution.
Okay, so summing up the impact of FR3E.
In essence, FR3E gives us a really robust, structured way to handle exploration in RL for LLMs. It's smart about finding those uncertain points, exploring there, and using that adaptive feedback. And the result is models that train more stably, can reason more coherently over longer steps, and ultimately just get the right answer through the right process more often.
Especially for these generalist models, it seems.
Yeah, it seems particularly effective at boosting their reasoning ceiling. It's a significant advance in how we fine-tune these models for really tough multi-step tasks.
So, stepping back, what does this mean for you our listeners, the researchers, the engineers working with LLMs. This work really pushes forward how we can get models to tackle complex problems.
Right.
It highlights that it's not just about scale, more data, bigger models. It's also, crucially, about smarter learning strategies.
Smarter training.
And this ability to automatically find and explore uncertainty within the model's own thinking process, that feels like a powerful new tool in the toolkit for building more reliable and capable AI systems. Systems you can trust more on complex tasks.
Definitely.
You know, this whole idea of uncertainty-driven exploration, it feels very human, doesn't it?
It does, yeah. We often focus our learning where we feel unsure.
Exactly. So here's the thought to leave you with. As we keep pushing LLMs into even more abstract areas, maybe scientific discovery, maybe truly creative problem solving, how could methods like FR3E evolve? How might we apply this idea of structured exploration to tackle even fuzzier reasoning challenges? Or maybe even cross-modal tasks, where images and text are involved, where identifying those uncertainty points might not be as simple as finding a high-entropy word in a math proof.
That's a great question. How do you define and target uncertainty when the state isn't just text?
Right. Something to think about as you work on the next generation of AI.